Now we're going to be going over the activity and we'll answer questions. Okay, so chapter 14, activity 1. Right, hopefully everybody's watched the video at least until 16 minutes and 10 seconds and possibly tried the activity already. So the first part is about ether nomenclature. And ethers are like halogens. They have no priority in terms of nomenclature, and they're never named something with an ether as part of the parent. So it's always a substituent, basically, kind of like a halogen. So if there's other functional groups, you would name it like the other functional group, right? For example, like an alcohol. If there is not, then you would name it like an alkane or an alkene or an alkyne. And then there's a IUPAC way and a common way. So for the two here that can be done both ways, I'll give you two names that are IUPAC accepted. Names for. Okay, so the IUPAC way is to look for the longest carbon chain, and that would be there's one carbon on the side and two on the side. So the longest carbon chain is this 2 carbon chain. And then we'll number it 1, 2, because we want the our only substituent, right, which in this case is a methoxy group, to come at the lowest number possible. So then this becomes 1, and sometimes the 1 is left off. So if you don't see a number, it's assumed. You can always add it. 1 methoxy, and then it's named as an alkene. Again, ether is part of the substitution. So 1 methoxyethane. But because this is a simple ether, you can also do it via the common way, right? And that would be calling it an ether, and then the 2 alkyl groups become the, quote, substituents on the oxygen ether, and they go in alphabetical order. So this is a methyl and an ethyl. E comes before M, so it would be ethyl, methyl, ether. 3 different words for that way. Okay, and in this case, this is not a common alkyl group. We can't name it the common way. So we're only going to do the IUPAC way. And we're looking for the longest carbon chain. We want to number it such that our substituent gets the lowest number possible. Okay? And in this case, we have a chiral center you have to pay attention to. So in terms of priority, the oxygen, the alkyl group to the left, the alkyl group to the right. I usually just draw a little arrow. The hydrogen is pointing back, it's counterclockwise in S. So we have S at the beginning, then our substituent, 3-methoxy. So the ether is named as if, look at how many carbons there are, and then the methyl becomes methoxy. So 3-methoxy hexane. Carbon alkene, that's the parent. Okay, the next one we can do via the common method or an IUPAC method. For IUPAC, we're looking for the longest carbon chain, which there's a tie here, right? Because we could do 1, 2, 3, or 1, 2, 3. So that's a tie. But if we go from this direction, now we have more substituents. So not only do we have a isopropoxy group, but we also have a methyl. That's the tiebreaker. So this is going to be the correct parent. I numbered 2 substituents. So we have methyl and isopropoxy in the I count in alphabetical order. Okay, so 2 iso. Normally you would call it an isopropyl, but it comes from isopropoxy. 2 isopropoxy. 2 methyl. So the methyl group at carbon number 2. And then it's named as an alkane in this case. Or or more simply, for the common way, we could remember that this is called an isopropyl group, and the one on the right is called a tert-butyl group. We could place those two names in alphabetical order, followed by the word ether. So for tert-butyl, the T doesn't count, right? Because that's a counting group. It's only the B does. So it's B versus I. So B comes first. So we're going to do tert-butyl, and then isopropyl, followed by the word ether. And they're three separate, in this case. Okay, the last one has both an alkene and an alcohol. Alcohols have the greater priority. So we're going to name it like an alcohol. When we do that, we have to start counting at that carbon because we want the lowest number possible for the group with the highest priority. Then we might go, okay, what's next, right? The alkene or the substituent. And the alkene is next because it's also part of the parent. So we're going to count 1, 2, 3, 4, 5, 6. And there's 2 chiral centers here. So doing a quick 1 to 2 to 3. We have a 1 to 2 to 3. Hydrogen pointing back, that's R. And then that's too fast, try it on your own. Okay, and then hydrogen pointing back, so that's S. So putting that all together with our stereochemistry at the beginning, we would do, I don't know if it gets more. Better. Okay, 1. Yeah, better.
So the alkene, you went that for the numbering of the cyclohexene, you went like to the left there, circling around, or counterclockwise because the alkene would take priority?
Yes, because it's also part of the parent. The parent is going to be a cyclohexene all. So the alcohol has the highest priority, but the alkene is also still part of the parent, so it gets the next highest priority. And then the substituent, which would be the lowest priority.
Got it, thank you.
Okay, so 1R, comma, 6S, parentheses. Okay, and then we only have 1 substituent. So that is the 6-methoxy. Oh, sorry, that is an epoxy. And now we have the parent, right, which is the cyclo, and I would just keep going here, but no spaces or dashes or anything. Cyclo, hex, and then I need to do the 2E-1 all. So this 2 could come before the C in cyclohexene, so it could be 6-ethoxy 2-cyclohexene 1 all, cyclohex 2E 1 all. That's optional. And there's no way to do a common. Any questions with nomenclature before we move on?
Do you have to put the 1 all, or can you just say, you know?
You don't have to. Yeah. Anytime there's a 1, it's technically optional. And on. So the next part of this is the Williamson ether synthesis. This is one way to make ethers. Williamson ether, the name reaction. Add the name. And that starts with an alcohol. All of these are alcohols. And it utilizes a strong base to deprotonate the alcohol. And the left over here, I'll show you the mechanism. The first one. So take the alcohol and I'm drawing some lone pairs since we're drawing the mechanism. And then sodium hydride. It is important to use a strong base in order to fully deprotonate the alcohol. It needs to be a stronger base than, for example, hydroxide. So sodium hydride is the most common choice, or you could also use sodium mix. So the point of the hydride is it's a strong base, it will deprotonate the alcohol. We're doing a proton transfer. What we call an alkoxide. This forms hydrogen gas as a byproduct, which would just bubble out of the solution. And then we can add in an electrophile to basically do an SN2 reaction. So we're going to be adding in here methyl bromide, like CH3, Br. And this does an SN2 backside attack. Take out the bromine, bromide. We would get the product here. Product of the first. This is just the only really limitation here is that the alkyl halide needs to be either methyl or primary. And that's because you are doing an SN2 reaction. So for an SN2 reaction, it is best if it is a very unhindered alkyl halide like methyl or primary. Secondary, while that can work for an SN2 reaction, it doesn't work in this case because the alkoxide is also a strong base. So elimination competes substitution. And elimination is the major. We use this sort of strong base / strong nucleophile on a secondary alkyl halide. So it has to be methyl or primary. Limitation. Okay, so this is going to be the product. We'll star there, so I don't have to redraw it. And then the next one, so the stereochemistry isn't really changing. Okay, so we just kind of copy it over. This one, we're adding, instead of a methyl, a normal propyl. So we'll just draw in a propyl group. Or you could write it as PR or NPR. Okay, so this is the one that is not actually going to do synthesis. And the reason for that is this alkyl halide is secondary alkyl halide. So it's not going to do an SN2 reaction with this strong base / strong nucleophile. It will be once we deprotonate it. Let's look at what happens there. And see the mechanism, because it asks us to write it anyway. We're going to start with our alcohol, start with sodium hydride. That will do a deprotonation as expected. Okay, and then now we have this alkyl halide. That's secondary, and the problem is that this, while it can act as a nucleophile, this is extremely bulky. This is a bulky group. And so that makes this not really act as a nucleophile. Instead, it acts as a base. And it's just too sterically hindered to get into this carbon to do an SN2 reaction, especially on an alpha carbon that's already secondary and sterically hindered. So the major pathway will be acting as a base, and because it's a bulky base, we'll do a E2 reaction that favors the Hoffman product. So we'll selectively take the hydrogen that's less sterically hindered, as opposed to a hydrogen here, and we will end up with alkene. So basically we did an E2 favoring the Hoffman product because of the bulky base. Yeah. Okay, so that's the product, which is not what you might expect. So it did not undergo. Instead, it just did an E2. Any questions on this?
Could it also react with a hydrogen that's on the opposite side?
Over here.
One more down.
This one, it will not, because this one, you cannot form an alkene by deprotonating one of those.
Okay.
So we'll only take a proton in front of the two beta carbons in order to do the elimination. And this is the alpha carbon. These are the beta carbons. This is the gamma carbon. It's too far away. So it would take a proton from one of the two beta carbons, but because it's a bulky base, it will prefer to take the less sterically hindered hydrogen, ending up with a less substituted alkene. So we say this, it undergoes Hoffman regioselective. Answer your question?
Yeah, thanks.
On. So we're looking at the alkoxymercuration demercuration reaction, which is very similar to the Markovnikov hydration reaction. So that basically, instead of saying alkoxymercuration, we used to call it water, we called it a oxymercuration. So the only difference is, instead of adding water in the first step and making the Markovnikov hydration alcohol, we add alcohol, and then we end up with an ether. And it still undergoes Markovnikov regioselectivity, which basically means look at the two carbons. This one is more substituted, so the ether ends up there, and the smaller hydrogen group ends up with the less substituted. This is our second method for producing an ether. Right? So if we don't do a Williamson ether, we can do this alkoxymercuration demercuration. There are some advantages to this. Remember the limitation with the Williamson ether reaction. The problem with it is that the alkyl halide has to be methyl or primary. So you're limited in the types of ethers you can make because of that limitation. Whereas there isn't as much of a limitation on this reaction. So it has an advantage in that way. So let's look at some examples that don't have R groups. I hate R groups. They don't look, they're confusing, right? So we want to look at like some actual examples here of the reaction. Okay, so when we're looking at this, here we see it is an addition reaction of an alkene. And it's going to work similarly as if we were doing hydration, where we would get an OH group, right? But instead of that, we can get an ether, because instead of using water, we're going to use alcohol in the first step. Notice that the group here, the so-called R group, the alcohol, ends up at the more substituted position on the alkene. And then on this carbon, less substituted one just gets a hydrogen. So that's often not even drawn in. So essentially this carbon just got a hydrogen, which we didn't see. And then because we use methanol, we end up with and the mechanism, he doesn't really go into it at this point, but I guess it was gone over last semester probably. Or if you'll recall, we ended up forming for example, if I do it for the first one, we ended up forming the mercurinium ion. You may have heard of this one before. Which, instead of having a full positive charge on the mercury, this bond sort of lengthens and it shares the positive charge on the more substituted carbon here. And so that's why the water, or in this case an alcohol instead of water, that reacts very similarly, will preferentially attack that more substituted position. And we'll kick out the mercury, the leaving group. Then we will end up with that mercuric acetate on the less substituted carbon. And the initial product of that step would be something like this. This proton is just removed through proton transfer. And then this mercury is removed using the sodium borohydride step. The hydride replaces it, basically. And that's why you end up with it. So that's the mechanism, and the attack at the more substituted carbon because of the delta positive is the reason for this. Okay, so let's see if we can do a few more examples. So this one, we just have to pay attention to what group we're adding here. Okay, so it's a phenoxide. And then, of course, it's going to go on the more substituted carbon. Okay, and the other carbon. We can just draw that out. Let's sketch out the carbon backbone. And then put our OR group here. The other carbon got a hydrogen. There's no stereochemistry here. Don't have to worry about that. So over here, we look at our R group, adding an iso-epoxy group. And this is the more substituted carbon. So it's going to go there. I can just sketch out the backbone and then do isopropyl. Okay, moving on. So this one, he got a little bit tricky, and he just switched these two, the positioning. So instead of seeing the alkene over here and the alcohol over there, he just switched it. And it doesn't even matter which one goes where. Right? We just have to kind of pay attention to that. So we have the alkene is here. That's the more substituted carbon. So that's where I'm going to end up putting this alcohol. So I end up with a butyl group and alcohol. So that's just a little bit of a switcheroo. And looking over here, so now he took the alcohol or the other reagent away in that position. And he's basically saying, okay, there's two components. There's the alkene and the alcohol. So you provide me the one that isn't there to make that product. So looking at this is where the more substituted position, so that's where the alcohol would have ended up. That's the alcohol I've added. So over here, I've been given the alcohol and not the alkene. Okay, so I can just go, okay, where did that alcohol come from? That alcohol came from there, which means that the other carbons were part of the alkene. So there's actually two options here. This is sort of the carbon backbone. This needs to be the more substituted carbon. So there's two ways to do that. And I could put the alkene here, or I could put it. Both cases, you would get the same product, right? And this is the more substituted carbon, so that's where the alcohol will end up. Any questions on this page before we move on?
Yeah, I had a quick question. Can you also put, instead of a double bond, an alcohol there on the ring?
So the
Yeah.
alcohol is here. That's why I did an alkene. You need two components for this reaction. You need the alkene and the alcohol. So because he said this is one of the reagents, and it's an alcohol, that means that the other one has to.
Okay, but you can't use 2 alcohols.
No, because the mercuric acetate is going to react with the alkene to form the mercurinium ion. You have to have an alkene to form that mercurinium ion, and then the alcohol attacks.
Got it.
So we're continuing on this page with that reaction, and sort of thinking now retrosynthetically. How could we have made, for example, this ether through that alkoxymercuration demercuration? So he's highlighting that potentially we could have made this bond or the other one. And depending on which one you're making, right, that changes the reagents. So for example, if your goal is to make this one, that means that the part on the left is your alcohol, and the part on the right here has to have been your alkene. And if you were trying to make the other side, the other carbon-oxygen bond, then that means that the alcohol, the carbon chain on the right, and then the carbons on the left had to have come from the alkene. So there's 2 different alkoxymercuration, demercuration reactions from different reagents that would work to make that ether. Okay, so that's the idea. And the next question says, a student proposes that the following 2 alkoxymercuration, demercuration reactions produce the same desired product. Explain if the student is correct. So from this one, remember that the alcohol group is going to go on the more substituted carbon. So this would have actually been installed here, not here. This one doesn't work because this assumes that the alcohol group can be installed on the left of it. Over here, we have the more substituted carbon and the alkene is this one. That means the alcohol would get installed there. So if we use butanol, then it becomes a butoxy group at this carbon. That one would actually work. So this one works. So it's just being careful that you would actually get the product that's shown, given the 2 reagents that are chosen, making sure to understand that the alkoxy group will go on the more substituted carbon always. Okay, so synthesize the following from an alkoxymercuration demercuration. So in this case, we only really have one carbon-oxygen bond that we can form. And that would be this one, because this is only a 1 carbon. So you can't have an alkene on this side with 1 carbon. So the alkene then must have come from this side. So that simplifies to methanol has to have been the alcohol, and then the alkene propene, and that works because the methanol would have gotten inserted into that more substitute. So those 2, plus of course you need to remember the correct reagents for the mercuric acetate, sodium boron. Okay, so in this case again, this side is only a methyl. So we can't make that bond through the alkoxymercuration demercuration reaction. Because if we did, that would mean that this carbon would have to have been an alkene, which is not possible. So the only bond we can make with that one. So that simplifies to the alcohol must have been methanol. Right? And then if we make that one, and think of this, sort of sketching out the carbon backbone of the 1, 2, 3, 5. And then we have to insert the alkene, where this is the most substituted position. There's 2 ways to do that. Either this one or here. Both of those have that carbon as the most substituted. So either alkene plus methanol plus the correct conditions work. Okay, so looking at this one, we have a bond to a phenyl group, and then a bond to a tertiary carbon. You can't make this bond to a phenyl group because the carbon attached here is sp2. That would not work out. Because it's already a double bond. If you had another one, it would be like a triple bond. It wouldn't work. Okay, so that means that you have to have had that part alcohol, and that simplifies to 5 members in the whole group, where again this carbon is the most substituted carbon. So in order to do that, you have 2 choices. Would the double bond inside or outside? All right, last one. Now we have 2 carbon-oxygen bonds, but this is the only one you can make through the alkoxy mercuration demercuration reaction. That's because this carbon is primary. And if it's primary, it won't work because the alkene would have been here, in between these 2 carbons, and this would have been the less substituted. And the alcohol would never end up on the less substituted. That wouldn't work. So you have to instead have this part on the left be the alcohol, which would be by the way, by the time you write this conditions many times, you pretty much have it memorized. Okay, so this is the only option because this is a primary carbon. So note how the bond you make, right, is always to a more substituted carbon, secondary or tertiary. So it doesn't work to make it to primary phenyl. Carbon here is in S. Any questions on this? So this is kind of working backwards. How could you have gotten this ether from an alkene? So the next part is provide a mechanism for the following reaction. So this, we call this acid promoted, sometimes people might call it strong acid promoted ether cleavage. So one of the things about ethers is that they're not very reactive. So you're not going to see a lot of reactions of ether. So far we've covered how to make an ether, right? You can do that through the Williamson ether synthesis or through alkoxy mercuration. Those are the 2 main methods. And now we're getting into, okay, what can you do with an ether to make something else, right? And the answer is not a whole lot. Ethers are very stable, right? And so that makes them great solvents, by the way. Because typically you don't want your solvent involved in the reaction. It needs to be there just to facilitate the collision between reactants, stabilize transition states, intermediates, but not necessarily react itself. Okay, and they have very low boiling point, and so they're easy to remove after the reaction. Ethers are very common solvents, and part of that is their lack of general reactivity. So the only thing you can really do to react a simple ether that's not an epoxide, which we'll talk about eventually, is this acid promoted ether cleavage. And the reagents for that will either be HBr or HI. So it has to be HBr. And typically it doesn't mention it, but you also have to heat the reaction. So, and that's because ethers are just very stable. But what you can do is you can break these two carbon-oxygen bonds in that reaction. And it will break as long as the carbon attached to the oxygen, okay? And there can be two, same or different, as long as they're sp3. So this is sp3, sp3. We can break both of them. If it was sp2, we wouldn't be able to break that bond. So for example, you can imagine there's a phenyl on one side. So in a case like this, but you would only be able to break this one if this one is sp2. So you would not be able to break this one because that carbon. Okay, and that's because we're relying on substitution reactions, SN1 or SN2, and those require an sp3, hybridized carbon tool. Back up here, we have ether. I'll redraw it so you do all of it. We're going to draw the mechanism with excess HBr. So it's a strong acid. It's possible that it already reacted with water and formed hydronium ion, and that's the acid in solution. That's possible. Or it could just be reacting with HBr. I'll just draw HBr instead. So the first step is a proton transfer. Since it's a strong acid, it's very likely to donate its proton to the oxygen. Proton transfer. Now the oxygen is positively charged, which, by the way, makes the two carbons attached to the oxygen much more electrophilic, because now this oxygen is a good leaving group. Right? So the carbons attached to it are actually very. And we form some bromide in the first step. So bromide can now do an SN2. This is a methyl group, so it's very unhindered, very great for an SN2. So this step is, you might just label it SN2, but of course you know SN2 is both a nucleophilic attack and loss of. And then now we've broken one of those bonds. We have an alcohol, methyl bromide. And it can keep going. So there's more, notice the excess HBr in this reaction, so there's more HBr around. And just like it protonated the oxygen of an ether, it can protonate the oxygen of an ether. We end up basically doing the steps over. Another proton transfer, creating a good leaving group, and some bromide. And with the secondary carbon, remember that it really undergoes both SN2 and SN1. Right? So it's possible, the mechanism would be correct if you drew SN2 or SN1. So with SN2, you would do both nucleophilic attack and loss of a leaving group. With SN1, you would have the leaving group leave first, form a carbocation, and have the nucleophile attack. And it's probably undergoing a mixture of those two mechanisms. Right, so either is really okay. I'm just drawing it as an SN2, mainly because Dr. Wynn did. They're really exposed. And in this last step, we formed some water. So in the end, we ended up cleaving the ether, both carbon-oxygen bonds, forming two alkyl halides and water. I wouldn't say this is a very useful reaction, because how did we make the ether in the first place? From an alkyl halide, most likely. Now all we're doing is going back to an alkyl halide. But it's the only thing you can do, because ethers are so stable. So again, it says draw the products, right? And with very strong acids like HI and HBr. So this one is HCl, not HI or HBr. So no reaction. And then next we do have HI, which is good. And we're going to look at these two carbons. Note that they are both sp3. Great. That means we can break both of those bonds. And I can just count out this carbon chain to make sure the product that I draw, since it's not a ring anymore, still has the right number of carbons. And so I'm just going to do 7 carbons. 2, 3, 4, 5, 6, 7 phenyl. And then at carbon number 2, I end up with a iodide. Also at carbon number 7. Plus water. I broke both bonds. So again, that's just figure out where to put it just by doing some quick counting. Okay, and then the last one, a little bit more tricky because there's 2 ethers, and all of the carbons attached to the oxygens are all sp3. So I really can break all of them. So you end up with, oh, we're doing VR here. Change that, and end up with bromine and 2 waters. There's a lot of cleavage going on. There are at least 4 equivalents of HBr. Any questions on cleavage of ethers with HBr, HC?
I'm a little bit confused with the identifying if the carbon is sp3 or not.
Okay, yeah, so okay, so we have so this carbon has 2 hydrogens attached, an oxygen, and then a methyl group. So this, we would call this having a steric number of 4. I don't know if you've heard that term before. Steric number of 4. But basically, the steric number is the number of sigma bonds, right, plus the number of lone pairs. There are no lone pairs on that carbon, but it would be included in the steric number. So because this carbon is making 4 different sigma bonds, it has a steric number of 4. Anything with a steric number of 4 is sp3. So basically, to make 4 bonds, it had to hybridize its 2s orbital and all 3 of its 2p orbitals to get 4 new sp3. Whereas on this side, this carbon is only making 3 sigma bonds and has no lone pairs. This is a pi bond, so one of them is pi bond, one is a sigma bond. Sigma, 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 no lone pairs. So this carbon will only hybridize to sp2. That's because it only needs to make 3 sigma bonds. And when it does that, it will have one remaining unhybridized p orbital. And that unhybridized p orbital will make the pi bond. So pi bonds are side-to-side overlap of unhybridized p orbitals. So when I say the hybridization, it has to do with the steric number. And that tells me the hybridization. Does that make sense? More? Do you want me to go over that more?
No, that makes sense. So then you're saying,
Yep. So it has to be sp3, but it doesn't have to be primary. So for example, both of the carbons on this side, both of these are F, because this one is making 3 sigma bonds and a 4th sigma bond here. So 3 carbons and 1 oxygen. This one is making sigma bonds to oxygen, carbon, and 2 hydrogens. Either way, they're both making 4 sigma bonds, 4 atoms attached. So they're both sp. So you could cleave both of those in a ether cleavage. But for the one up here, you would only be able to break this bond because this carbon is sp3. You would not be able to break that bond. That carbon is sp2. Because think about how the reaction is taking place, right? In order to break this bond, I've got to do an SN2 or an SN1 of that carbon. You may have learned from last semester, you can't do an SN2 or an SN1 reaction, a nucleophilic substitution, at an sp2 hybridized carbon. So it just doesn't work out, and so you can't break that bond. So, for example, and I don't know how much he went over this in the video. I go over it in my YouTube videos, but I notice sometimes he sort of simplifies and doesn't necessarily go over every single thing, which, you know, is good and bad. Okay, so anyway, if you had this one versus those 2 examples, and you were doing HBr, and even if it was excess doesn't matter how many equivalents you add. Then the products, because we're only cleaving that bond, the products are ethyl bromide, and then this, that 1 carbon oxygen. Whereas here, I can cleave both. So I end up with 2 alkyl halides, tert butyl, ethyl, and water. Water only forms if you break both carbon oxygen. Can I move on? Are we okay with that? Yes. So back here, we're going to start doing some synthesis. Okay, so we remember that, right? We want to look at and kind of analyze the entire reaction before you get started. So we are going to be adding in, right, this oxygen and these carbons over here. So this part of it was added. And then these carbons are present in the reactor. So we're going to be making an ether, so it's very relevant to this chapter, right? And we look and see, okay, remember, how many methods do we have to make ethers? How many reactions? Nobody wants to answer. there's two, right? There's the Williamson ether and the alkoxymercuration demercuration. So which methods can we use here? Well, in order to answer that question, I need to look at these two carbons that are attached. If one of them is methyl or primary, one or more of them is methyl or primary, you could use a Williamson synthesis. But I have secondary, tertiary. Because of that, I can't use a Williamson. So that means that I have to use the alkoxymercuration demercuration process. No Williamson. Again, it would have to be a primary or methyl, potentially using Williamson. Okay, so then starting in the forward direction, start with our alkane. Remember that there's only one reaction you can do with alkanes. When you start with an alkane, okay, your first choice has to be a radical halogenation reaction. Alkanes are very unreactive, like ethers, so they don't do anything except for radical reactions. So now my bromine will end up in the more substituted position. So that's how this works. But if I want to do an alkoxymercuration demercuration, what does my starting material have to be? It has to be an alkene, because I already am going to add this alcohol. I'm adding the alcohol later. So I need this half to be an alkene. So my goal then is to make that alkene, because that's one of the reactants I need for an alkoxymercuration. So in order to do that, I can just use any base, bulky or small doping in this case. There's no competing substitution on a tertiary carbon. It's strong base. So no SN2 base. So any base works. Okay, so from here, this is the more substituted carbon. That's good because that's where I want my alcohol to add in. So I'm going to draw in the alcohol that I want to use. Conditions for the alkoxymercuration demercuration. I wrote those out a million times before, so you should have it memorized. The mercuric acetate and sodium hydride, and that will produce the product. Don't hear any questions. Start analyzing. Again, we're making another ether, and definitely going to be adding some carbons. Okay. When we think about what side is going to be added, it's a little bit confusing because we've got these three carbons, which really could have come from the left-hand side, or they really could have come from the right-hand side. You've got some options here. They're both the same carbon backbone. It's just here it's attached to the most substituted. Here it would be attached to the less substituted. That's some options. And then if you're thinking about, okay, I'm going to use a Williamson ether potentially in this one, or an alkoxymercuration demercuration. Well, that depends, right? Let's look at the two carbons attached here. So what do we notice about the carbon? We have, on this side it's tertiary, on this side it's primary. If it's primary, you can use a Williamson ether. So you can potentially use a Williamson ether to make that bond. To make this bond, because of this is primary, you cannot use an alkoxymercuration. Right? But if you wanted to make this bond, then you can use an alkoxymercuration because it's a tertiary carbon. So tertiary or secondary, you can use an alkoxymercuration. Primary has to be Williamson. So it depends sort of on what you're going for. We can draw out some different possibilities here for synthesis. Just because it says to provide one path doesn't mean there's only one path that would work. There are sometimes many paths, and the more reactions you learn, because we go on to more and more subsequent chapters, the more possibilities there will be. You'll have more reactions to choose from. Okay, so let's say that we are going to try to go for the Williamson ether. It doesn't matter. So remember, I'm starting from my alkane. Because I'm starting from an alkane, I only have one choice. No matter what, I have to do radical halogenation. So it makes it easy because so from here, if I'm going to be doing a Williamson ether, I'm going to make this bond. That means that this has to be the alcohol. That means I don't need an alkyl bromide. I really need alcohol. This is the alcohol that's flipped over. So if I can get that alcohol, then I can do a Williamson ether where I deprotonate it with a strong base, and then I add in the alkyl halide that's primary. So it works for the Williamson ether. So once I've targeted that alcohol, I can do the Williamson ether. So notice I didn't write anything in here yet. That's just because I felt like doing the last step first. There's no, just because I know I need to do this doesn't mean I have to write in the reagents. So then I go back and go, okay, how can I do this? I know I need to do it. Can I do it in one step? The answer is yes. Right? You can do an SN1 reaction with water. Because it's a tertiary carbon, right? It's a good leaving group. Bromide would leave, water could add, and then, or you could do two steps. You could do an elimination and addition reaction to get to the alcohol. Either way, but it can be done in one step, so that's what I wrote. Okay, so that's the Williamson ether approach. And then what about if I had targeted potentially doing an alkoxy mercuration demercuration? Let's give another alternative. So if I want to do that, I'm going to be making this bond over here, right, which means that this needs to be an alkene. This is going to be an alcohol that I add in. So really, you could get the alkene, add this alcohol, right, or make this alcohol and add this as an alkene. There's so many options on this one. So just keep going and keep going. But let's say we want to make an alkene. So we'll start here. And we want to do, again, we have no choice. And then if I want to make the alkene, I can do my alkoxy mercuration demercuration. I just need to do an elimination. And any base works, bulky or not bulky, because it's a tertiary carbon. So once I do this one, then I can go ahead and do an alkoxy mercuration with alcohol. That one. So the other option is from this targeting making the alcohol. Just add in the alkene as the other component. So if I had wanted to make that alcohol, then how could I do that? Basically, I go from here to here. The same first reaction. And if I want to do that, I have to do an elimination followed by an addition reaction. So I need to make the alkene anyway. Then I could go from the alkene to the alcohol. So I need to make the alkene with the base, do 2. And then this is a anti-Markovnikov hydration reaction. So if you remember, to do an anti-Markovnikov hydration, you need BH3 followed by sodium hydroxide, or hydrogen peroxide. So, and then if you wanted from there, you could do your alkoxy mercuration with adding the alkene. It's really so many possibilities with what you could have drawn in this one. Okay, that's a lot. That's a lot of possibilities. But if you had worked on this in advance, I wanted to make sure to show a lot of different options. So maybe one of what you drew matched one of these with the others. And I don't want you to think just because you don't have exactly what I have, it's necessarily wrong. It might still be correct, even though it isn't what I have. All right, so moving on to the next one. This one, there's also a lot of possibilities. I came up with at least 3 options earlier, what you could do here. We'll go over lots of options. But basically, you want to make this diol from the alcohol. And because we're going to be making a new carbon-carbon bond, and in some way, shape, or form, we need to make that carbon-carbon bond because we'll be adding this in. Then I'm probably going to have a problem with this alcohol being unprotected. Because what are my choices for making a new carbon-carbon bond? Right? I either have to do an alkylation with an alkyne, which requires protection of that alcohol, or a Grignard reaction, which requires protection of that alcohol. So probably no matter which one I choose, I have to protect this alcohol first, and then we'll deal with this. So if we protect, remember conditions are TMS chloride in the main base. To show it protected TMSO, the alkene. Now it depends on if you want to use an alkyne or if you want to use a Grignard. And even if you want to use an alkyne, there's multiple ways you could do that. Okay, so one of the ways you could do it is to convert this alkene into an alkyne, then add the carbons. So to convert an alkene into an alkyne, it's a 3-step process that was taught last semester. So first of all, you have to do a bromination. Then you have to do a double elimination. And then you add in some water to pertonate. Those 3 steps from the alkyne chapter get you from a double bond to a triple bond. Notice how I didn't bend the triple bond. It's linear, so draw it that way. Okay, so from here, now that I have a terminal alkyne, I can do an alkylation. I can add in 2 more carbons. And the easiest way, because I also need this alcohol, is to actually use an epoxide. So what I can do is I can use a strong base, and you've seen this alkylation before, but you've probably never seen it with an epoxide. So it can actually attack ethylene oxide. So if I deprotonate here and make an anion and a lone pair, I could do an SN2 on the epoxide. And then So this is getting into epoxides, which technically we're not really covering until next week on Monday. Okay, so this might be a little bit strange, and you probably didn't come up with this one, but it's a possibility. So what would happen here just mechanistically, and you don't have to draw this, but just so you helps you. The first step deprotonates terminal proton there, and then you do an SN2. Then we need a acidic workup, which again is sometimes left off. But that would get you to that compound. And now all we have to do is reduce the triple bond and get rid of the TMS. Dr. Wynn, basically, if he includes an acidic workup, he just gets rid of the TMS in that same step. And that's fine. It's possible that that happens. If not, you could just always at some point do TDAP. Notice how, right, I should double check I have the right number of carbons. I need 1, 2, 3, 4, 5. And I have 1, 2, 4, 5. I should always double check that I have what I need. So I just need now to reduce the bond all the way to a single bond. And to do that, I'm going to use catalytic hydrogenation, which was in the alkene chapter last semester. Hydrogen gas and the catalyst. Catalyst could be palladium, platinum, nickel, a lot of different metals. Okay, that's one option. More are kind of going over on time. I've told you I like to do today. Not kind of, really going over. Okay, so the next option you might have done is maybe you did what Dr. Wynn did. Follow that. So TMS chloride and triethyl protect. He converted this to an alkyl halide. He did an anti-Markovnikov addition of HBr across the double bond. That will put the bromine at the less substituted position. And then he just took, because he knew he was adding 2 carbons anyway, he just said, okay, I'm going to add an acetylide ion to that. It will do an alkylation and kick out the bromine. So he did this to add the triple bond. Then he needs an alcohol here. So he didn't write 9-UVN. I don't know why he went boring. Usually with an alkyne, you write 9 instead of pH 3. So that one does the anti-Markovnikov hydration, which leads to enol, which then tautomerizes to. This is a review reaction again. Remember, there's lots of reactions from the first semester that you still need to know. So from here, you might remember that you can reduce an aldehyde to an alcohol using LAH or sodium borohydride. I'll use sodium borohydride because it's easier to work with than LAH. And then I just have to remove the TMS group. So TVAP or H3O plus. Okay, that's option number 2. One more. And that's using a Grignard. What if we wanted to use a Grignard? So I'm just going to start from TMS protected. No matter what, you would have to TMS protect instead of writing that out again. Just start there. So if I wanted to use a Grignard, my choices are I could convert this to an alcohol and oxidize it to an aldehyde, or I could just convert it to a bromide and then add in a different electrophile. I think I'll choose that. So we're going to do the same thing we did before. I want to convert it to a bromide, anti-Markovnikov hydrohalogenation. Get me here. And then instead of adding an alkanite ion, I can go ahead and convert this to a Grignard reagent, magnesium. That will form the Grignard reagent. Now I can add in an electrophile, which the best one will be the epoxide. Again, you'll see more use of epoxide from the next set. So that would, the Grignard would attack here. Reaction like an alkyne would. Just have to unprotect. Or you can just assume it got unprotected. I get extra carbons here. 1, 2, 3, 1, 2, 3. All right, another. Okay. That was a lot. Did anybody come up with anything different than that they want to talk about? Well, there's lots of options for how to do that. All right, last question in this one, which is a mechanism question. So this has been used in the chemical literature to make an epoxide. Well, one thing we know with Grignard reagents is that they love to attack carbonyls. So they definitely like to do a nucleophilic attack on that ketone. So we have after the nucleophilic attack, that's just showing that attack. And then the idea is basically we're doing a Williamson ether, but within the same molecule. Because now we have an alkoxide and an alkyl halide. This is a little bit weird because you have to show an SN2 reaction on a tertiary carbon, which we usually don't do. But because it's intramolecular, potentially it's possible, especially if that chloride is really starting to come off a little before the alkoxide came in. Okay, so this is kind of a weird SN2 reaction, but we're just proposing a possibility that happen. And that would produce. So it's essentially an intramolecular SN2. It is a little bit weird that this carbon is tertiary, but the only other option is showing loss of a leaving group first, so carbocation. I think that's unlikely to happen with an alkoxide right next to it. Probably that's helping it leave. It's probably somewhere in between SN2 and SN1. The chloride is kind of leaving a little